everybody. Welcome to the last day of KVM Forum. Just a few quick introductions. My name's Alex Bennée. I work for Linaro. Mostly, I'm interested in ARM stuff, and I tend to spend my time working on TCG, so on the emulation side. But you will find me occasionally working on KVM. So what are we talking about today? TCG plugins are a way for people to run experiments, taking advantage of the fact that when you're running stuff under emulation, under TCG, you have complete and utter control of the system. So you can literally examine the system state every single instruction that you execute. But before I go into detail on that, I just want to talk a little bit about the history of plugins in QEMU. Bit of a warning, there are some dragons here. So when Fabrice first wrote QEMU, he didn't really intend to do a plugin system. He considered plugins something that you really need for closed source projects, and QEMU definitely wasn't. And also, early on in the project, he didn't want to have the problems of dealing with binary compatibility or defining a stable API. But I mean, that statement was in 2004. It didn't take long before people were suggesting some sort of plugins interface. Win4Lin was an example of a fork of QEMU that was designed to run Windows on Linux. And what they've taken is chunks of the QEMU source code, made it able to load plugins dynamically. And the idea that they were going for was to have proprietary plugins to emulate bits of hardware. As you can imagine, this caused a little bit of discussion on the mailing list. They weren't actually doing anything wrong, because back in those days, the bits of QEMU they'd taken to build their Win4Lin project were all under fairly liberal BSD licenses, and it's a good lesson in reminding yourself of exactly how your project is licensed. But again, moving on to 2005, someone suggested possibly doing a plugin interface just to mimic the PCI interface, so you can make it easy to trivially do a device model that followed the standard PCI API. And by the time we get to 2007, there was a GSOC project called PyQEMU, and the idea there was you could implement machine emulations in Python. But the response from the community was, sorry, but no. So a couple of lessons that we can learn from this. I mean, these are all examples of hardware emulation. And one thing, the QEMU community is very wary about anything that can be used to evade the license of the project itself. There are worries about API stability, because as soon as you introduce a plugin API, you're then putting some strictures on your own code and limiting what you can do in terms of refactoring and doing things internally. I mean, this is one of the arguments the Linux kernel has. They don't have an API for modules. They reserve the right to break it all the time. But this is a solved problem now, at least for upstream. We have enable modules, which allows you to build the QEMU source tree with all your hardware emulation in modules if you want, and load it up and dynamically. And I think that Paolo's talk will talk about the configurability. So we don't need to worry about that aspect of it. However, this is not the topic of the talk, so let's move on. This is a banyan tree. So this is a type of fig that grows on other trees, so it uses them as scaffolding. These can get quite big. The nest of roots and branches can cover a couple of acres, and often they strangle their host tree. So during a patch that was suggested back in 2009, someone wanted to implement instruction counting for ARM. It was a very invasive patch. It was never going to get upstream, but there was an interesting comment made during the discussion on that there are three users at least three users for QEMU. So there's people that want fast simulation. There are people that want virtualization, the KVM guys. And there are people that like to use QEMU for instrumentation and research. But these three use cases are often in conflict. People are worried about adding instrumentation infrastructure will either slow down the common case, because most people just want it to run as fast as possible, or you'd end up with a code base that was full of if-defs, and then it becomes a maintainability nightmare. But the history of QEMU is replete with lots of forks. Most of these come from academia. So the QEMU project was part of Berkeley's BitBlaze toolset, so it was used for doing taint and security analysis. That was based on QEMU 0.91. decaf was an evolution of that on a slightly newer code base. PEMU was a fork of QEMU that introduced the PIN API. So PIN is a dynamic code instrumentation tool, I think by Intel originally, and they brought this into QEMU so you could run PIN tests. And QTrace was another approach that was more of a tracing approach that allowed you to trace the execution of, in this case, only x86. So the history of QEMU is littered with these academic forks. Another example, the first QEMU Users Forum back in 2011, there were a lot of interesting talks. If you want to know some of the stuff that people were doing with it, there's an excellent trip report that Peter wrote up. And they covered a wide variety of tasks. But there was interesting things like doing cycle-accurate simulation. It's one thing that QEMU doesn't really care about when it's emulating a system is how many cycles it takes, how many guess cycles it takes to do an instruction, because we just want to run things as fast as possible, and doing the accounting for that would be expensive. But there are also people doing program instrumentation, so they wanted to look at how programs ran, the sort of instructions they're executing, the sort of code paths they were taking. And also things like cache and pipeline modeling, so just working out what impact a program had on on the cache of the system and how you could change that. And of course, none of these are things that really QEMU as a core project is interested in, because they all get in the way of running as fast as possible. I'll just mention one of the many projects that were mentioned in that talk, and that's ATOS tools. So this is something that ST Microelectronics developed. It's still an actively developed project. It's completely open source. It's an open source fork. You can get it from their GitHub. And it's about 700 commits difference from the QEMU mainline. They actively merge to the current state of upstream. I think their last commit was a month ago. And it can do a number of interesting things. So one thing it can do is it can simulate hardware in user space. So they use this so they can write drivers using Linux user and develop in a sort of more friendly user environment before porting it to a kernel. Another interesting tool is this one called DynamoRIO, which is basically a cache simulator. So you can give DynamoRIO information about the size of your instruction data cache, and it'll track all the accesses going through it, and then give you information about your cache residency. So it's obviously very useful for them, and that's why they continue to maintain it. One of the reasons it's probably never been suggested for upstream, though, is it's fairly invasive. So all the tools that they write directly inject TCG operations into the stream. So if you're writing a plugin for this, you have to basically understand how the TCG works. So what's the conclusion we can take from all these examples? Well, there's plenty of demand for using QEMU for doing these sort of experiments. And who can blame them? QEMU is a very flexible program. It simulates a lot of different guest architectures, and it's one of the faster modeling systems around. And unlike things like Dynamo and PIN, it also works with system emulation. So a lot of these instrumentation systems only really work with user programs, and often you have to run on the same architecture as well. So QEMU is flexible. But there's a lot of these write once forks. A lot of the academic ones have been written as part of their academic research, so they're not particularly interested in getting stuff upstreamed. And if you can understand, if your job is getting research papers out, you don't have a lot of time to spend talking to upstream and molding the code to what upstream wants. So we've got a lot of code that's never going to be upstreamed. So with that, let's talk about the path to upstream for this. This is the Bolton Strid. There we go, back again. It's regarded as one of the most dangerous rivers in Yorkshire because it looks quite easy to cross. You can actually jump across it, but you really want to be sure you do it right first time because it's deceptively deep. And because it's deep and fast, there's a lot of underwater caves that you can get trapped in. Right, so the path to upstream. I think I'm going to start with Louis Villanova's original work. He did a lot of work to introduce support for the tracing infrastructure into TCG. So he introduced the concept of being able to have generation time and execution time plugins. And as part of that, there was a bunch of work done to introduce a common translator loop. So this doesn't apply to all the guests, but certainly all the main guests now use a common translator loop to minimize the number of places where you need to put your hooks in. He also did an instrumentation series, but that never got merged. Now, you can get a long way with logging. I mean, this is an example of running one of our test cases. It's a SHA-1 test. It just does SHA-1 on a block of memory. And those flags, I don't know if you can see there, -D CPU will dump the CPU state every time we come out of the execution loop. And no chain basically ensures that we come out the execution loop for every single translated block. So this is great. You can do a lot of analysis with this. But for that simple SHA test case, that generates 19 gigabytes of logs. So you need a lot of disk space. And even if you compress it, it comes out about 344 megabytes, right? So there's a lot of redundant information in that log. And imagine the sort of logs you generate if you were running something in the kernel. So you really want to be able to process this data dynamically. I suggested a series in 2018 that basically abused trace points. So I allowed you to load a plugin, and as long as a plugin had a function that was named the same as a trace point, it could hook into it and do what it wanted at that point. It was an interesting experiment. It didn't really go down particularly well with the other developers, mainly because it introduced a very wide API. And so it was all very well saying hook into the trace points, but trace points can change, so you don't really have any sort of API stability. And the trace points are quite wide and varied, so it gives you're digging quite deep into the internals of how QEMU runs. Pavel did a series, so this was an iteration of the ISP RAS plugins tree, which they had for their research. It introduced the idea of having a needs filter, so a plugin could have a needs function which would get called and it would say yes, no, and then it would hook in the helper function, so it could directly call a helper in the plugin. He presented these ideas back in 2017 and the RFC in 2018. And then the next iteration was Emilio Cotta. He did a series, similar sort of approach, but he was using it for doing his work into parallel computer simulation. So it supported direct helpers again, direct out of the TCG code, as well as inline operations, which are useful for doing some quick and low-cost counting. You could do instruction granularity instrumentation. I think one of the limitations of the original approach is it needed a two-pass translation, so that required a bit of tweaking to the translator to support that. He also had support for doing time control, because he wanted to make sure that the time in the simulation that was reported to the guest was actually what a guest would see rather than effectively the elapsed time. I'll talk a bit about that later. And he also had some guest hooks, so a guest could indicate to the plugin interesting areas of memory that it might want to look at. So what have we learned from these approaches? Well, the first thing, APIs are hard. People want to get an API defined that's not going to limit your further development and not leak too many internals is tricky. So let's talk about the actual implementation that we've got now. I assume everyone knows what Lego is, right? So the design principles of the current plugin interface, low impact. So the idea is that it's in the minimal case, when you're not actually doing any instrumentation, it's barely measurable. You can also disable it from the build if you want to get rid of it all, but if you're not actually subscribing to any events, it's pretty low cost. It has a very simple, non-leaky API. So everything that the plugin gets is in the way of opaque handles, which it can query bits of information about. But most importantly, for this iteration, no state modification as well. So the plugins can't be used to circumnavigate any GPL requirements. They're purely passive monitors of the system. So this is very much a sort of minimal viable plugin implementation which we can build on in future. So I'll just quickly run through how it works. So we have the normal run loop. We need to do a translation. If we don't have a translation, we generate one, we insert it in our code buffer, and then we run it. So the way TCG works is it works with these things called TCG ops. So a single arm instruction, add 120 to the stack pointer, breaks down into a number of TCG operations, which we can then use for the code generation. So in that pass, for each instruction, what we do is we add a dummy TCG call at the beginning and end of each instruction. Once we've gone through the block, we then give the plugin an opportunity to decide which events it wants to subscribe to. The events that it doesn't subscribe to, we can just drop those TCG operations. They won't ever get generated. And the ones that it does want to subscribe to, we replace those dummy TCG operations with real TCG operations to call the helper. There's an optimization phase, and there's a chance for the TCG to slightly improve the code, and then we generate our host code. So the plugin API, a couple of rules. Plugins have to be threading aware. TCG for a long time has been multi-threaded. We don't do any hand-holding for you, so if the plugin has shared data structures, it needs to deal with its own locking. The opaque handles I've already mentioned. These are only valid during the callback, so any information you want to get out, you need to copy into your own structures. So you need to do your own housekeeping. So all plugins will have at least one function, this QEMU plugin install. It gets a few bits of information. It gets a unique ID. You can have as many plugins running at a time. It gets a little info block, which tells it a minimal amount of information about the system. Broadly, it's the architecture you're running on. And some arguments, so you can pass arguments to your plugin. It will then set up its bits, and there'll be probably at least 2 callbacks it will want to register. It will want to register to the translation callback, which is the jumping off point for doing additional instrumentation, and the at-exit callback, so when you get to the end of your run, you can dump information out. So in the block, this is a translation block. Here it's just doing a simple instrumentation of each translation block. So at the start of the translation block, you can either jump to a callback, or we do support this thing called an inline operation. There's only one inline operation supported at the moment, and that's the ability to add a 64-bit number to a counter somewhere. But if you're just doing raw counts and you've got a single-threaded program, that's the simplest way to do it. A couple of pieces of information it can find out: the program counter at the start of the block and the number of instructions. So we've done that. So if you want to instrument the individual instructions, you can also get a list of these instructions. Again, these are opaque pointers, but for each instruction, you can then make a decision about whether or not you want to have a callback before it runs, or maybe just increment a counter. So there's a couple of helpers that you get for that. The instruction data, so this doesn't give you a peek directly into memory, it's just a copy, readable buffer of the decoded instruction, the size of the instruction, virtual address and hardware address, and you can, we've also added the ability to call QEMU's disassembler, because we don't really want plugins to have to ship an entire disassembler themselves when QEMU can already do it. For memory accesses, much the same sort of pattern, go through each instruction and register a memory callback. It doesn't matter if the instruction you're registering doesn't do any memory accesses. In those cases, those callbacks will never get generated, and you'll never get called. So basically, you just instrument all the ones that you want. You could always look at the instructions if you wanted. And then in the memory callback, you'll get another bit of information. So you'll get the CPU that the access was on as an index, and then another opaque data structure which you can query in the virtual address. So there's a couple of helpers. So importantly at the moment, you don't actually get access to the data itself. This is certainly something we can look in for version 2, but at the moment, you get the size of the access, whether it's side extended, is it a big endian or a little endian, is it a load or a store? And with that, you can actually do quite a lot of interesting experiments already. For system emulation, you can also take that virtual address and then find out where it maps to. So it will tell you whether it's an I/O access or not. and then give you the offset into the device. So if that device happens to be RAM, that will just be the offset into your RAM block. A couple of other APIs just to mention. There's a QEMU plugin outstring, which just allows the plugins to output its information via QEMU's debug output. So this is just better than plugins spamming standard out or standard error with their data. You can redirect it. Plugin reset and uninstall. So plugins can optionally uninstall themselves at any point. So it might be that a plugin has collected enough data. It can then unregister itself. We'll flush all the translations, and then we'll get that, and then you can it'll flush all the translations, and then you can just wait until the end and dump the information you've collected. Syscall return for user space and vCPU for when vCPU is coming in and out. So I'll just rush to the very last few slides. There's a bunch of example plugins. We've got basic blocks, instruction counters, memory counts. And then with the hot ones, hot blocks allow you to measure execution, residency. Hot pages, you can look at what pages are seeing most reads and writes. And HowVec is basically an instruction classifier. Future work, do we want to access more system states? So at the moment, we don't allow the plugins to access system memory. We'd also like to access registers. The trick there is coming out with a decent API that's going to be nice and general enough and doesn't expose any internals. So I think previous APIs have used things like GDB, stub register IDs, but that's a bit messy. Finally, we expect you to be able to use this for developers. It'll be useful as well, for developers as well. So one tool that I'd like to write in the next cycle is a lockstep execution. If you're a TCG developer, you spend a lot of time looking at instruction traces. You spend a lot of time trying to work out what you broke, why the program worked on a previous one version and doesn't work on another version, and you end up doing lots of diffs of trace files. So with a plugin, it's actually be quite trivial just to make something that allowed 2 QEMU processors to run in lockstep. I briefly mentioned time. Time at the moment is a function of effectively the wall clock time on the host. So it means the emulation overhead is visible. So if you're doing experiments that you're trying to look at what a real behavior of a real system will be, you'll find that timer interrupts are occurring more frequently than you would on a real system. Now we do have a solution for this. It's called iCount, but iCount's not multi-threaded, and even then, iCount really is just pegging the amount of elapsed time to the number of instructions you've executed. So if you wanted to do real simulation, maybe the option there is to expose that to the plugins, or even allow the plugins to control the passage of time, because then the plugins can take the time to work out exactly how many cycles will have passed. So, in summary, it's been a long journey, but we now have a common non-invasive interface, which is very efficient in the null case and is ripe for expansion. I don't think this is going to lead to the end of all these outer tree forks, but I'm hoping now going forward that any outer tree forks will be building on a common base, so their diffs will be smaller. All right. Sorry for the speed of that, but any questions?
So we have time for one quick question.
You mentioned in-tree and out-of-tree plugins. So in-tree, it's obvious, but out-of-tree, I guess the interface is not stable, so you're tying yourself to a specific QEMU version, do you?
Yeah, I mean, I don't think we're planning to keep changing the API interface just for the hell of it. It's fairly simple and general enough. But yeah, if you want it to always work, I would suggest get the plugin in tree. But there will certainly be academics that will want to be doing more detailed, more invasive plugins that maybe want to expose more information than we're comfortable in the upstream. I'm just hoping that their diff will be a minimal diff to support that, with a common code base for basically injecting the instrumentation. Okay.
Okay, so thank you.
Okay. Thank you very much.